Alright, so let's take a look at Bayes' rule. This is a rule that I'm sure you've covered before in your probability and statistics courses, right? It takes this conditional probability and converts it to a product of three other probabilities, two unconditional probabilities and one conditional probability. And at the beginning, this seems sort of absurd, right? You're taking a simple thing and making it more complex by factoring it into three terms. Let's take a look at what these terms mean. We've colorized these terms for you on the second slide. What we're trying to calculate is over here, right? This is what we're going to call our posterior, right? We want to know that given some evidence that we have from our data matrix, what's the probability of a certain class, right? Our y values. And to do that, we're going to flip the probability around and look at it from the other side. So paying attention to the right side of the equation, we can see that we can convert this without any loss to the idea of a likelihood. The likelihood says, given that we have a class value, let's say that the concept is liked, okay, a drink is liked, what are the chances that the data is being observed, okay? So if I presume that you like something, okay, what's the chance that this particular drink is being liked, okay? That's an idea of our likelihoods. Okay? Then we also have a class prior. Okay? This prior is basically how likely overall, unconditionally, that the concept holds, right? So for example, in our concept learning case, we could think of the idea of whether a drink is liked or not. Perhaps you have particular picky friends who don't like a lot of drinks, so their prior is lower. Unconditionally, without knowing what they want to drink, you already assume that they probably don't want to drink anything, okay? But you might have friends where the prior is very high, right? That they are always sweating or always wanting something to drink, and so their PY would be considered high no matter what type of drink it is. We also have this third term here, which is the marginal, right? This is the probability of a particular data item. You know, whether a certain type of drink exists in a particular place, for example, would be considered a marginal. So to put it more formally, let's go to the next slide where we've put all the notation here very clearly. Great, so now that we have that out of the way, we can also look at this other rule that you've seen many times in statistics, which is the idea of the probability chain rule or product rule. The idea is to take a particular event and view it as a joint probability of many other events. Okay, and these are joint probabilities because they have a comma, right? So it means all of these things are happening together to produce the particular observation that we see on the left-hand side. Now, when we view it as a product or joint probability of different events, we can also think of it as a vector, right? Our typical standard way of looking at a data matrix. So we have this vector of different features, then we can decide which feature we want to care about first. It doesn't really matter. We can factorize this joint probability any way we'd like. Okay, so we could take off the first term, for example, and say, given all of the rest of the terms, x2 through xn, what's the probability that given that x1 will occur, right? So this is the posterior that we're looking for, okay? And then because we factored this out, we no longer have to deal with x1. We can just deal with all of the rest of the joint probability parts, x2 through xn, independently of x1 because we factorized it out, okay? So obviously we can repeatedly apply this idea to factorize x2 off, x3 off, all the way until we have a single unconditional probability of the very last factor, okay, which is our p of xn rather. And of course, because the notation is invariant to which one is called x1 or x2, you can factorize any way you'd like. So let's come back to Bayes' rule and look at naive Bayes. Naive Bayes is a particular learner which uses Bayes' rule, hence the part of the name that deals with Bayes, but in a naive fashion. Hence the other part of the name, right? So naive just means that we take this joint probability, this x1, comma, x2, comma, all the way to xn, and treat it in a more simplistic fashion. We're going to make the assumption that the features inside of this joint probability are actually conditionally independent of each other, given the actual class value. Okay, so we've taken the joint probability of x, and we factorized it into all of these smaller parts, right? So we're taking each component of x, x1, x2, all the way to xn, and think of those as independent of each other. They have no bearing on whether they are influenced by each other if we know what the class is. Now, this assumption usually doesn't really hold in practice. If you have two different features that are correlated with each other, they're not conditionally independent. Think of, for example, measuring whether it's raining outside and looking at features like whether somebody's shirt is wet and whether they're holding an umbrella. Obviously, these two features are correlated with each other. But for the purposes of naive Bayes, we're going to assume that these two features are uncorrelated with each other and they independently predict the class. Okay, now we also have the prior, which is what we saw before, like how likely is it to be raining outside in general in Singapore, or how likely is it that your friend likes a particular drink? That still exists for naive Bayes. We're going to use these two terms, the original prior and a naive formulation of the likelihood, multiplying these two terms together to get an idea or approximation of the posterior. Now let's be careful about this. This is not Bayes' rule, so this equal sign is actually not equals. This is an approximation, okay? But we're missing one term, even with the naive assumption, and that's our marginal, right? The probability of the data. Now, where did that go? We have to think about that for a second. So I'd like you to pause the video for a second or two. Think about why is it that we don't need the p of x in this formalism. And then I'd like you to move on.